These are the notes on plate tectonics, the way that the surface of the Earth forms and changes. In order to understand plate tectonics, it is necessary to understand what lies within the planet Earth. There are many different ways to divide up the interior of the planet, but the simplest one is usually adequate for most purposes, and that is dividing it into these layers seen here. The outermost layer is the crust, which is a very thin layer, even thinner than I've indicated here. Underlying that, we have the mantle, which is the thick red layer that makes up most of our planet. And then below that, we find the core of the Earth, which is divided into two separate parts, the outer core and the inner core. The outer core of the Earth is a liquid, whereas the inner core is a solid. Now this deviates from what you would guess, because usually you'd expect, well, if it gets hotter and hotter as you move to the center, then we expect the liquid to be under hotter conditions. However, because the pressure is also increasing towards the center, that is why we find a core that is solid below an outer core that is liquid. Now, the composition of the core of the Earth is well known to be made mostly of iron and nickel and several other very heavy metals. The other layers of the Earth, the mantle and the crust, are made of similar things, primarily silicates, which are made of silicon and oxygen. And that's really what the Earth is made of. And then there's a very thin layer of ocean, of course, and a thin layer of atmosphere around that. And that is what the Earth is made of. If we think of these four layers, we can understand plate tectonics fairly well. One analogy I like to use to help remember what the layers of the Earth look like proportionally is to take the circular cross-section of an avocado. If you cut through an avocado in the direction that makes a circular cut, what you find is somewhat close to the proportions we find in the Earth. The crust would be the skin of the avocado, the mantle would be the green fruit, and the core would be the pit. The only problem here is the core is not subdivided into an inner and outer core. But that's usually pretty close. Now, of course, avocados vary. Sometimes the pits are larger. Sometimes the fruit takes up less space. It varies. But for the most part, that's a pretty close analogy to the structure of the Earth. Also, the great thing about this is you can really get the sense that the crust of the Earth is so thin compared to the other layers, just as the skin of the avocado is very, very thin indeed, with little bumps indicating the topography. Another way to divide up the Earth is to talk about where rocks act like rocks, like what we're used to, and where rocks do not act like the rocks we're used to. Okay, in this sense, we could talk about the lithosphere, which is similar to the crust of the Earth, but it does include a small portion of the mantle below it that still acts pretty much like rocks we're used to. Then there are several phase transitions that occur with the structure of the silicates that affect the way that they move around, the way that they are flexible, or the way that they are brittle. And in the asthenosphere, which is just below the lithosphere, that is where the material is able to move the most quickly. Now, the problem with this is that, oh, you're thinking of material moving sounds like a liquid, but actually, for the most part, the materials that are moving are still in solid form. It's just they're moving ever so slightly over many millions of years, which can make major differences over geologic time. So the misconception that often occurs here is that people like to think of the mantle as being a liquid because it does move. But solids can move over great periods of time. There's a number of ways they can do this. one atom can shift over, then the next atom can shift over, and eventually the whole thing has moved. In this situation, we have many more layers, including the upper mantle, the lower mantle, and for the most part, on a high school level, we do not need to deal with these specific layers. There's also something called the MOHO, the Mohorovich zone, which is where you get a major change in the way the seismic waves move through the mantle of the Earth. But for the most part, we're going to stick with the 4 layers I mentioned earlier, but just be aware that there are different ways to slice it. Plate tectonics was originally proposed by a man by the name of Alfred Wegner. Now, the problem with Alfred Wegner is that he was not actually a geologist or a physicist. He was actually a meteorologist. He was a German meteorologist. He studied weather and climate. But along the way of studying weather and climate, he noticed many, many things, pieced them all together, and came up with the idea that the continents had to be moving. The problem he had was that he had no way of explaining a mechanism by which these giant, massive continents could be made to move around the surface of the Earth. And so geologists, especially because he himself was not from their field, kind of laughed it off, and it was not accepted, unfortunately, until well after he passed away. He actually passed away examining the ice in Greenland on an expedition there, which, as you can imagine, can be a pretty risky endeavor. If you're a meteorologist, you're often looking at maps, and you might notice some things, like about, as many people have mentioned, that the east coast of South America and the west coast of Africa line up. Another thing that people don't always seem to notice is that the east coast of North America also lines up with northwestern Africa, and that's a pretty good matchup as well. And then a number of other things led him to conclude that the continents had to be moving. He just had no way of explaining how they did that. The hypothesis that was proposed was that continents had at one point been part of one landmass and had since separated. This turned out to be correct. However, landmasses had been together multiple times in the past, even before that. Because it turns out it's kind of like on a conveyor belt where they go one way and the other way, separating and then colliding again and again in a long, long cycle. So the concept of Pangea, which is now well known, is that all of the continents, or at least most of them, were interconnected at one point about 250 million years ago, and then they rifted apart and formed the continents we have today. This video shows the separation of Pangea into Laurentia and Gondwana land, and then eventually those separating into the continents we have today, the 7 recognized continents that we designate today. Notice that throughout different periods of history, different continents have been in different locations on the Earth in terms of the equator and the poles. So they've been at different latitudes, different climates, sometimes tropical, sometimes temperate, sometimes even polar. A piece of evidence that really helped Wegner's hypothesis was how identical rock formations could be found separated by a giant ocean, like some of the Appalachian Mountains in the East Coast and some of the Caledonian Mountains in Europe. They were almost identical rocks formed at the same period of time, and he suggested, well, wouldn't it make a lot of sense if they had formed as one big mountain range? And in fact, that is how they formed. Okay, but again, geologists had other ways of explaining this. They suggested, well, maybe the rocks that formed at that time were just like that, something like that. Another piece of evidence that he had observed was that there's evidence of glaciation in places that today would never have glaciers, especially in India, which is fairly tropical, okay, and you would never expect glaciers, at least except in the highest mountains in India today, but there's pretty good evidence that there have been glaciers there. So that indicated to Wegner that, oh, maybe India has moved from a polar climate to a tropical climate. Now, geologists could say, well, maybe there was just an ice age that was so big, it covered the entire planet. And so even tropical places were cold enough at that moment to get glaciation. And that is, of course, a possibility. But it's another piece of evidence that suggested that maybe the continents have moved. So even though he could not give a mechanism for how the plates were moving, there was quite a lot of evidence, even in Wegner's time, that the continents had moved. One piece of evidence is the continents appear to fit together, and that has been noticed by many people, even before Wegner's time, but no one had been bold enough to suggest that maybe they actually had been together. Fossils had been found on continents on opposite sides of the ocean, like in South America and Africa, suggesting that maybe those had been together. For that same exact species to live on both continents is very unlikely otherwise. Glacier distribution, as we mentioned, in places like India that are now tropical. Glaciers in India? But unfortunately, that was not enough evidence to convince geologists. It wasn't until they mapped the ocean floors using sonar after World War II and then did a bunch of other surveys of the ocean floor that the magnetic bands were discovered. It turns out the magnetic bands on the ocean floor were the one clinching piece of evidence that geologists could no longer deny, and then they had to accept plate tectonics. So plate tectonics really was not accepted until the 1950s. The 1960s is really when it was fully accepted. So long after the time of Alfred Wegner, who passed away in the 19-teens. Magnetic bands, there's no other way to produce them other than making new crust and having it separate. Okay, this also gave rise to a hypothesis for how the plates were moving as well. So unfortunately, the other pieces of evidence were not enough to convince people, but the magnetic bands were the strongest piece of evidence, the undeniable piece that confirmed the theory of plate tectonics. We now know that the crust of the Earth is divided up into many separate plates that move in different directions relative to each other. It's really hard to say which one is standing still. There's really none of them that are standing still. So all we can really talk about is their relative motion compared to each other. What's happening between any two plates that are next to each other? You may notice that they're not all the same size. Some of them, like the Pacific plate and the North American plate and the Eurasian plate, are gigantic, although let me point out that this is a Mercator projection. So a lot of what you're seeing at the very, very top and the very, very bottom of the map is heavily exaggerated, making those plates look a little bigger than they actually are. In fact, the Pacific plate is by far the largest plate on the Earth. And then there's some very, very tiny plates. The Juan de Fuca plate, the Caribbean plate, the Cocos plate, those are very, very, very tiny. And there's even some that it's a little debatable about whether they're really separate plates. Like the Indian plate and the Australian plate have been relatively connected for a lot of recent geologic history. And so whether they are considered separate plates or not is a little bit of a debate. Not to mention, there's the little Scotia plate down at the bottom of South America. So notice that they're all different sizes and they're all moving in different directions. So when you talk about the way plates interact, you really have to talk about the boundary between any two neighboring plates. So the crust of the Earth is broken into many pieces called plates, which are moving relative to each other. Whenever you find a large shifting of these plates, that is where you are likely to find the largest earthquakes, like the largest earthquake that has occurred in my lifetime, the one that occurred in Japan in 2011, the 9.0 earthquake that ironically occurred where the North American plate meets the Pacific plate. Well, guess where we are, guys? Here in Southern California, we are where the North American plate meets the Pacific plate. Even though Japan is on the other side of the ocean, it's the same two plates. Interesting, right? But you might be surprised to learn that we are actually on the Pacific plate, not the North American plate. Japan, on the other hand, at least part of Japan, is located on the North American plate. So isn't it funny that Southern California is on the Pacific plate, whereas northern Japan, part of Hokkaido and Honshu, are located on the North American plate? Very strange the way these plates wrap around the Earth, isn't it? So what kind of relative motion are we talking about here? There's three different kinds of relative motion that plates can have with each other. The only other option is if they're not moving relative to each other, which probably means they're part of the same plate now, and plates can actually be welded together and merge. One of the ways that plates can move relative to each other is transform faulting. A transform boundary is where the two plates are sliding past each other. Neither one is going toward or away from the other. They're just scraping alongside, like two ships going in opposite directions that scrape along the side in a canal maybe. Or if you have two tables next to each other and you pull one backward and they're scraping along each other, that is a transform boundary. This is the kind we have in California with the San Andreas Fault, which actually is a plate boundary. The second kind of plate boundary that we can find, kind of motion, is divergent. When you diverge, you separate. When you're diverging, so when the two plates are moving apart from each other, well, the problem is that they can't leave behind an empty space between them. So what winds up happening is that is where new crust may be formed. Okay, this is a very important part of plate tectonics because you need some way to generate new crust. That is where crust is generated. On the other hand, when two plates are moving toward each other, that is called convergent. They're converging like a car crash, two cars driving right into each other. Okay, a convergent boundary, you can have a few different kinds of this, but this is one of the places where crust can be destroyed, let's say. Okay, a great example of this, the best example in the world, is the west coast of South America. Just along the west coast of South America, there's a convergent boundary that has been going for hundreds of millions of years. I think I forgot to mention that the great example of the divergent boundary that is often cited is the Mid-Atlantic Ridge. That is just a great example of a divergent boundary. So you can have more than one kind of convergent boundary. One of the types of convergent boundary, a very common one, is convergent subduction. When you have convergent subduction, what's happening is a piece of continental crust is moving toward a piece of oceanic crust, crust that is under the ocean. Whenever this happens, the oceanic crust always loses the fight and sinks below the continental crust, and it winds up going beneath it. At some point beneath the continental crust, the subducting plate is what we call it, the oceanic plate that is going downward, is getting hotter and hotter and hotter, and it actually begins to partially melt. Now, the funny thing about this is it melts at a position in the Earth where it's not actually hot enough to melt those materials. The thing that allows it to melt is a little bit of the water that it brought along with it. So it turns out plate tectonics is heavily dependent on the presence of water on the surface of the Earth. It would be very, very different and very stalled out if that water wasn't present. And then when the rock partially melts, it turns out it changes its density. It rises up through the crust, generally producing large volcanoes, what we call a continental volcanic arc. And that is found inland from the subduction zone. Now notice that that is not actually found at the plate boundary, but it is a product of the plate boundary, and it's usually found near the plate boundary. The distance that occurs depends on the angle that the plate is subducting. Very typically, it is found about 100 miles inland. Now, what you find here also is a little bit of mountain building along the edge of the continental crust, where an island was sort of smacked on to the coastline. You also find this very frequently. Those are called coast ranges. Those form by the friction between the subducting plate and little islands that get scraped off of the ocean plate and then added to the continent. Another feature that is not shown very well in this diagram, I admit, is the trench, which is right where the subducting ocean plate meets the continental crust. That is generally the deepest place in the ocean, although I'm not showing it on here as being particularly deep. And it's the deepest places we find in any of the oceans of the world. So when you get subduction, one thing you know is it's always convergent. It always involves an oceanic plate, and then often it involves a continental plate. It turns out it doesn't always involve a continental plate. A good example of this kind of subduction is in Oregon and Washington and Northern California. So what we're doing here is we're looking southward from over the state of Washington, and that's the Columbia River there. And what we see is off the coast, there's a trench. Of course, that's under the ocean, so we can't really see it. And then all along, at various distances from the trench, we find the continental volcanic arc, which is formed from the melting crust that has now risen up through the continent. And examples of those volcanoes in this particular case would be, of course, Mount Rainier, Mount Hood, Mount St. Helens, okay, Crater Lake, and Mount Shasta. An even better example is in South America. Here we have east up, sort of, and we're looking along the west coast of South America, and that's a very well-defined trench there. Very, very well-defined trench, you can see. And the continental volcanic arc that has formed are the Andes, the largest volcanoes on the Earth, or at least the highest elevation volcanoes found on the planet Earth. And those have been forming volcanoes on top of volcanoes on top of volcanoes for hundreds of millions of years. So it's no wonder that they've reached those ridiculous altitudes. In particular, Mount Aconcagua is the highest of them. There's Mount Aconcagua. Another situation you can have that is also subduction is when two oceanic crusts are heading toward each other. Well, it's hard to say who's going to win this fight. Who's going to go underneath the other one? Well, it turns out there's an easy way to tell. Whichever piece of crust is older is the one that is going to lose the fight and go beneath the other. This is because over time, oceanic crust cools and becomes denser. So whenever you have brand new crust, as you're going to see how it forms a little later, it's going to be just a little bit lighter, a little bit more buoyant than any older crust. So when they do move toward each other, then the older one is always the one that subducts beneath. And then, of course, because it brings the water along with it, it still partially melts, and then it rises up, and it does also make a string of volcanoes. But these volcanoes are not on a continent. They are coming out up off the ocean floor. So what they wind up looking like is volcanic islands. So what we get is a volcanic island arc. So when you have subduction, if a continent is involved, then you get a continental volcanic arc. If no continent is involved, if it's two ocean plates, then you get a volcanic island arc. A good example of a volcanic island arc forming here, see how they're forming off of the ocean floor, okay, would be the Aleutian Islands in Alaska. That's a really good example. So you still get a trench, and again, I'm not showing it deep enough as I should in this diagram, and these tend to be the deepest of all the trenches because they're already down below the ocean, both plates are. So when one goes below the other, it's often super deep. So the deepest places on the ocean floor are these trenches that form when you have oceanic plate subducting under oceanic plate. As I mentioned, see all those little red triangles there? A lot of those are part of a volcanic island arc, the Aleutian Islands, that really long peninsula that stretches out from the bottom of Alaska. And they are forming as a volcanic island arc from the subducting Pacific plate under the North American plate. Hey, just like we saw in Japan, and it's the same two plates that we have right here. Here's what it looks like. Here's some of those Aleutian Islands. They're just beautiful, very, very active volcanoes that are rising up from the ocean floor. And they have that very characteristic shape of a stratovolcano, which is the kind that is associated with this type of volcanism. There's one erupting. They erupt very frequently, but the population in the area is relatively low, so it doesn't always get into the newspapers. It doesn't always get on TV when one of these erupts. They're going off all the time. The other option is, what if two continental plates are moving toward each other? Well, that's convergent, but now what you get is called a collision. It turns out continental crust is too low density, too rare to ever subduct into the mantle. So when two collide, the only option is for them to smash together and buckle up and down like an accordion, making a very, very large mountain range. Okay? When this happens, the crust thickens dramatically, both above, where you can see it, and below down into the mantle. Think of it as like the root of the mountain. This is how some of the largest mountains in the world have formed. In particular, the Himalayas and the whole Tibetan plateau formed like this from a collision between the Indian subcontinent and the rest of Eurasia. So remember, if it's two ocean plates, you're going to have converging. You're going to have subduction. If it's an ocean plate and a continental plate, you're going to have subduction. Only when it's two continental plates will you get a collision. So there it is, the best example in the world of collision right now on Earth. Although this has happened many times in Earth's geologic history, this one is still happening, and the Himalayas are still rising, and the Tibetan plateau is still rising from this collision. And of course, the highest mountain in the world today, Mount Everest, and the second highest, K2, are part of this collision. They are the highest point from the buckling up and down of the rocky material from the two colliding continental plates. This has been occurring over the past about 30 million years, and it continues today. It's about the same amount of time that the San Andreas Fault has been active. And you can sort of see how much mountains you can build in that amount of time. It's kind of amazing. And with the San Andreas Fault, you can see how much displacement you can get over that amount of time. So a lot of things can happen over 30 million years. So once you've had a collision, eventually the collision stops, and then the two continental plates are then welded together. So this is one way that you can build larger continents, and it's one way that Pangaea was put together before, of course, later it was pulled apart. So collisions happen as well, as we're going to see, continents can also separate. Another great example of a convergent collision are the Alps in Europe. Here in this picture, you can see the top of Italy at the bottom there, the top of the boot of Italy, is ramming into the rest of Eurasia, and it is forming the Himalayas. You can really see how they've buckled and folded, how it wraps around there, and it forms that really nice Po River Valley there below. So that's another great example of continental collision, convergent boundary collision. And here's a picture of the high Alps, which of course have formed because of that collision. And one of the most famous ones, especially in California, I think, is the Matterhorn. Now, the Matterhorn was uplifted because of this collision, but then another thing that makes it look so unique is that it has been sculpted by glaciers that have scraped and sharpened the sides. So one reason that it has that really cool, almost pyramid-like shape is not only because of the collision that has lifted it up, but the glaciers that have scraped it and sharpened it. The next one is the divergent boundary, where two tectonic plates are moving apart from one another. When this happens, and we'll talk about the reasons it happens later, when this does happen, it cannot just leave a space on the surface of the Earth or under the ocean either. And so what happens is material rises up and replaces the separating plates, forming brand new crust. This is where the new crust on the surface of the Earth forms from a divergent boundary. This is called an ocean floor ridge. So the feature is called a ridge because the volcanic material that is forming on either side of the boundary, or right at the boundary really, is a little bit higher than the surrounding ocean floor. So as you approach it from either side, it rises up as a ridge. It's actually two ridges, and the divergent boundary is right in the middle between them. So this is happening under the ocean floor, and it is possible at these locations, due to the hydrothermal vents, for a process to occur called chemosynthesis, where you can have life pretty much separated from sunlight, not dependent directly anyway on light from the sun. This is a really interesting process that was discovered at the ocean floor ridges. So most divergent boundaries happen on the floor of the ocean, and you get new crust forming. As the crust forms, it's very hot, it's very low density and rare, and then over time it will cool and become denser. It turns out that there's only so much density it can acquire before it wants to sink into the mantle below. It actually will eventually become the same density or even a higher density than the material that it is resting on top of, which is technically still the lithosphere, and then it will take a dive. And that's another process that drives plate tectonics. It turns out we have not located any ocean floor crust on the Earth that is over 180 million years old, which isn't that old considering the age of the Earth. So the ocean crust is being formed. It's the newest crust, but it's also the first crust to be destroyed. It's a lot harder to destroy continental crust than it is to destroy ocean floor crust. So it's basically forming and being destroyed all the time. Did you notice previously in the convergent boundaries, all of the plates that were subducted, all the plates that went down into the Earth were actually ocean floor plates. So this feature, known as the ridge, is the characteristic way to locate ocean floor ridges, and you can see them very easily on a map of the ocean floor. If you look at a map of the ocean floor, they stand out and they sort of run around the Earth. They look like the stitching on a baseball. They run around the Earth pretty much connecting with one another. So the problem with ocean floor ridges is they need to be almost perfectly straight lines. The surface of the Earth, of course, is a sphere. So divergent boundaries on the ocean floor ridges, cannot be continuously connected because of the geometry of the Earth. So what you need for them to form is little connections in between that are actually transform boundaries, which will be the last kind of boundary I will be discussing after we finish talking about divergent boundaries. I'm not done yet. So really, whenever you get divergent boundaries, you also get some transform boundaries along it, but I will explain those a little bit afterwards. They're sort of an offset where the plates are sliding past each other. Here's an example of a Google map of the ocean floor, the mid-Atlantic ridge in the middle of the Atlantic. And you can see that the divergent boundaries, which are shown in green, are offset by yellow transform boundaries. That's just because the Earth is a sphere. If the Earth was flat, then they could all just be a straight line and things would be much more rectangular looking. The shapes of continents wouldn't be so curvy, let's say. So the Mid-Atlantic Ridge is the largest of the divergent boundaries on the surface of the Earth. It runs right from the top of the Atlantic all the way down near the bottom of the Atlantic. It's the longest divergent boundary. So if you need to picture one, that is the most famous one by far, the Mid-Atlantic Ridge. The Mid-Atlantic Ridge, however, runs through one piece of land. The piece of land that it runs through is Iceland, the country of Iceland. Now, it doesn't run through the middle of Iceland. It runs off on the side there. And there's a lot of interesting things going on with the country of Iceland. It's a very unique geologic feature, actually. And when it runs through land, well, you can't really have an ocean floor ridge if it's running through land. So what we find there is a different kind of boundary when divergent boundaries are splitting up what is basically dry land, or let's think of it as continental crust. Okay? And what you get there is actually referred to as a rift, okay, or a rift valley. Now, Iceland has some other things going on. It does have a hotspot as well. So if you think about it, what's happening on Iceland is it's being ripped apart and separated into two different islands. Now, one of the islands would be much, much bigger than the other, but it is being like rifted apart. And this only happens when a divergent boundary passes through dry land. Now, this is not the best example of a rift. There's a much better example. But before we get to that example, let's talk about what's happening here when a continental plate is being pulled apart in two directions, forming a divergent boundary. This is actually how they initially begin forming. Well, what happens is a whole bunch of normal faults will form. Normal faults allow the material, the part of the crust that is closer to the boundary, to drop lower and lower and lower, forming a rift valley, as you see in the second diagram there. And then eventually, if that continues dropping lower and lower and lower, you would expect it to fill with water if it's the lowest point around. And then eventually that can become an ocean floor ridge. So a rift valley is really a transitional form, an early stage of a divergent boundary forming on a continent that will eventually form a sea. So we did see a whole bunch of this forming at the end of Pangaea, when Pangaea was rifting apart. This would have been how the Atlantic Ocean initially formed, in this way. But we see another example happening right now on the Earth. By far the greatest example we see today of a divergent boundary on dry land passing through a continental plate, basically forming a boundary that will separate that into two plates, is the Great Rift Valley in Africa. This is an example of a continental rift valley. It is located in Africa, specifically Eastern Africa, and you can almost see it if you just look at a map of Africa, where you see a whole bunch of lakes. The boundary runs down from the Red Sea. It comes down to the Red Sea, and separates off a lot of the eastern portion of Africa. Okay, what is forming here is a divergent boundary, and as it sinks lower and lower, of course, those portions fill with water, and you wind up getting a whole bunch of lakes surrounding Lake Victoria, the one in the middle, the biggest lake in Africa. And what we expect to see as long as this continues is that eastern portion is going to form into a new continental plate. Okay, it's basically going to separate from the rest of Africa, okay, and what will form in between them will be a brand new sea, okay, and eventually, if it keeps growing, an ocean. Because Lake Victoria is nearby, they already have a name for this future sea, the Victoria Sea. Okay, that's a pretty good name for it. And so a divergent boundary in the middle of a continent produces a feature called a rift valley. And in the rift valley, there's a lot of volcanic activity, heavy-duty volcanism that is forming there, and that is very noticeable in the eastern parts of Africa. There's all kinds of volcanic activity. A very famous one is the Ngoro crater, and it's not that far from where you find the giant volcano Mount Kilimanjaro. And so basically, Africa will eventually split in two as long as the continental plates continue moving the way they are now. Here's a little picture of part of the Rift Valley where you can clearly see the scarp on the side, the depression in the middle, and the fact that parts of it are filled with water, as you would expect. It isn't a sea yet, but someday it may well be. The last kind of plate boundary I can't really show you from the side because there's not too much to see from the side. So I'm showing you from above, like let's say an airplane view. And this, of course, is the transform boundary, more than meets the eye, right? So in a transform boundary, it's actually the nicest kind of boundary. It's the Autobot kind of boundary, no big deal. Two plates are just sort of scraping by each other, passing along on their merry way in two different directions. As if two different tables that are next to each other, one is pulled forward, one is pulled back, the boundary between them would be a transform boundary. Now these are generally the no frills, no problem plate boundary, the kind that can just pass by each other with minor bumps along the way, triggering minor earthquakes. That's the regular kind of transform boundary. But sometimes you have a problem. That is when the transform boundary has a bit of a kink in it, a bend. Well, what happens here is that notice what's happening when those two plates are sliding past each other. Notice what's happening right at that bend. You can sort of imagine that, well, it's really going to stick there, isn't it? Because right at that boundary, boom, there is a local collision. So a bend in a transform boundary can produce a local collision. By the way, it can also produce a local divergence if the bend were the other way. Oh, speaking of which kind of transform boundary is this? Well, if you step across the fault, the boundary, the plate you're stepping onto is moving to your right. So this is a right lateral transform boundary. And then, of course, you could just as easily have left lateral transform boundaries, okay, in different locations, just depending on the direction the plate is moving. Oh, notice how this one is a Decepticon. So yeah, this is the bad kind. If you have a transform boundary with a bend like this, where there's a local collision, well, that causes a whole heap of trouble, a whole world of trouble. And guess what? That's the kind that we have in Southern California. The San Andreas Fault, which is a transform boundary, has a bend very much like I'm showing here, causing a local collision. So the San Andreas Fault wouldn't be such a big deal if it wasn't for the bend that we see in Southern California. It's a little harder to see the bend because the fault is running diagonally here, but you can see it right above the yellow dot, which is where we are located. And that bend causes a whole heap of trouble. It prevents it from slipping smoothly with a bunch of small earthquakes and winds up storing it up into much, much larger earthquakes. And not only that, it winds up building the geography of Southern California. It winds up building the mountains and valleys that we find in Southern California. Might be easier to see if I turn it this way. Also, let's not forget about the other part of California, the part that is south of the border, the part where California was actually named from, Baja California, that 900-mile long peninsula that we can't forget about. That is the other part of California. And of course, that is also running along the San Andreas Fault. So if we want to see the entire length of the San Andreas Fault, the longest transform boundary in the world, it runs really from the very tip of Baja California down by Cabo San Lucas, all the way up to Cape Mendocino, which is in Northern California. That is not the Oregon border. It's south of there, but that's where the San Andreas Fault ends. It runs from the tip of Baja to Cape Mendocino, and notice that the biggest problem along there is that bend that is in Southern California. Now, I am also not showing a few other offsets that occur in the Sea of Cortez off of Baja California, but those actually go the other way. There's very small steps there that causes divergence, which is one reason that the Sea of Cortez is there, but I'm focusing more on the part that is near us, the step that is bending, let's say if you're moving northward to the left, which causes the big trouble. Okay. Now, of course, this is a plate boundary. So if you think about it, oh, it must divide two plates. So if the North American plate is on one side of the boundary, then what's on the other side? Oh, it is the Pacific plate. And notice that all of Baja California and all of coastal California, at least up to San Francisco, up to Daly City, is on the Pacific plate. So isn't it interesting that here in California, we are actually on the Pacific plate, okay, in this part of California. Of course, a lot of California is also on the North American plate, the more inland side of it, and if you get north of Cape Mendocino, okay? Whereas on the other side of the world, we already talked about that big earthquake that happened off Japan in 2011, and that was actually on the North American plate. And that was also a boundary between the North American plate and the Pacific plate. So these two plates have a lot of different interactions as you move around them. Here it happens to be transform, but in most places it winds up being convergent. And all kinds of different interactions can happen because of the geometry of the Earth. Think about the Earth being a sphere and all the different ways that these boundaries can interact. So if you didn't know it, we are on the Pacific plate here at Poly High. This is not the North American plate, sorry. And if you want to get to the North American plate, well, then you just simply have to go over the mountains and come down into the Antelope Valley, like where Palmdale is. As soon as you get to the base of those mountains, that is the San Andreas Fault, and everything after that is the North American plate. But we are moving to the north by northwest, and the North American plate is moving to the south by southeast, and we are gradually, over geologic time, shifting along next to each other, sliding along, and because of the bend in the fault, it's crumpling up this portion of California, forming the mountains and the valleys that we see around us, including the San Fernando Valley, of course. So if you look at the mountains and valleys, the Santa Monica Mountains, the San Fernando Valley, the San Gabriel Mountains, it's kind of like the compression you find along the side of an accordion or an accordion folder as you contract it. Parts of it go up, parts of it go down. Now it doesn't look quite as dramatic as it should because of the process of erosion. Okay, if it wasn't for the erosion, the San Fernando Valley would be significantly more jagged and deep, and the mountains would also be significantly steeper and higher. But because of erosion over time, it flattens it out and smooths out the surfaces, making it look like a relatively flat valley and relatively smoothed off mountains. But that doesn't represent the nature of what's happening here. It's a much more dramatic process. It just happens over millions of years, so there's time for the material to be eroded away. That is why we have so many earthquakes. And of course, you can see it from this picture as well. Okay, looking down over Burbank there, of course, from the Hollywood sign, the very famous iconic Hollywood sign. The reason all those mountains there are there and the valleys in between is basically due to the bend in the San Andreas Fault. Now, other than convergent, divergent, and transform boundaries, there's another major factor that determines a lot of features we see on the surface of the Earth. So I can't avoid mentioning this one, even though it is not necessarily found at plate boundaries. This one is called hotspots. Okay? A hotspot is generated by a hot plume of material under the Earth's crust. Now, why is there hot material there? We're not sure. It probably has to do with being heated by a hotter portion of the Earth's core below that. But then why is that hotter than the other portions of the Earth's core? We don't know yet. This is something we're learning about. But for some reason, the distribution of heat in the mantle and in the Earth's core is not even. Some places are just hotter than others. Because they are hotter, the material has a lower density and rises to the surface and works its way through the crust and forms volcanic features. While it's working its way through the crust, it is known as magma. When it rises out either on the surface of the Earth or under the ocean, on the surface of the ocean floor, it is called lava, and then it forms, of course, volcanic features like volcanoes, for example. Okay. A great example of this is the archipelago of Hawaii, the state of Hawaii. Okay. So it's basically a hot plume in the mantle creating volcanic activity. Now, Hawaii is nowhere near a plate boundary. It's almost as far as you could possibly get from a plate boundary, and yet it is a feature that is formed by plate tectonics. So plate tectonics primarily form features at the plate boundaries, but they can also form other features like hotspots anywhere. It can coincidentally be at a plate boundary, or as in the case of Hawaii, it can be way out in the middle of a plate. Okay, and it will continue to form the volcanoes, and as you can see here, they form above the hotspot, but then since plates are moving, that material is moved away from the hotspot, and then over time it settles and is eroded below sea level. So what you'll wind up finding is a volcanic island forming, and then over time as it is moved away, it'll sink below the ocean level and become what we call a seamount. A seamount is like an island that doesn't make it to the surface. It's like a mountain on the ocean floor that doesn't make it through the surface of the ocean into the air. And if you look at the Hawaiian Islands, it's a very clear example of this, where the hotspot is currently forming and currently having eruptions on the island, on the big island of Hawaii. And then all of the other islands have moved off the hotspot. They are having fewer and fewer volcanic eruptions and are basically eroding down lower and lower. So here is the Pacific Plate, and you can see that sort of long chain of islands and seamounts on the ocean floor. There's many others as well, but if you see the sort of unbroken chain that ends in the island of Hawaii, the big island of Hawaii. So why did it form like that? Well, the Pacific Plate is moving over the hotspot. The hotspot we can consider to be essentially in the same place. We don't know this for a fact, but if we consider this hotspot as stationary and the Pacific Plate moving above it, then of course it makes sense that you would form a series of volcanic islands that would gradually sink below the ocean, as the hotspot moves. Now notice where there is a bend right here. Well, that bend obviously represented a change in the direction that the Pacific plate was moving. The reasons for that would be complicated. It would depend on which side of the Pacific plate was subducting, etc. But look where the hotspot is now, where we find the biggest of the islands, just like we would expect. And then as you move further back away from it, you see islands that had formed earlier that have already eroded smaller. Some of them may never have actually gotten as big as the big island of Hawaii, but in any event, they've eroded from what they were in their heyday when they were sitting on the hotspot. And now the hotspot is in the process of moving off the southeast coast of the big island to form the next island in the chain, and that will eventually replace the big island of Hawaii. And it's going to keep on going for the unforeseeable future. We do not understand hotspots well enough to understand if they have a life cycle, if they eventually stop. But as far as we can tell, this one is going strong and will keep on going for many, many millions of years. Here's the big island of Hawaii and the other islands of Hawaii in the state of Hawaii. And the hotspot is right now moving off the southeast coast of the big island, and it's continuing to have most of its eruptions on the southeastern side on the volcano of Kilauea, okay? But then there was a recent eruption of the big one, Mauna Kea, okay, which is actually the highest point in Hawaii and one of the highest points in the Pacific Ocean. So anyway, it just keeps on rolling. So this map is showing many of the major hotspots located around the Earth. They're represented by the red dots. Now, many of them are not located anywhere near a plate boundary, but some of them just happen to be. So realize that that could be coincidental, or it could be that they help form plate boundaries. That is one thing that has been proposed. Okay, so look at some of these hotspots. Some of them are very famous places. Like Hawaii, we mentioned, very famous. The Galapagos Islands, where Darwin established the theory of evolution. The Azores, where Columbus stopped. We already mentioned Iceland. Now, Iceland is interesting because it does happen to be on a boundary. It's a hotspot that happens to underlie a plate boundary, which is one reason why there is an island there. Because if you think about it, if that's been a plate boundary for, let's say, 100 million years, you really wouldn't expect there to be any land there because it would have become an ocean floor ridge. But the hotspot manages to fight against that and maintain dry land, Iceland, the country of Iceland, right on a hotspot. Interesting, right? Another factor is we talked about the Rift Valley in Africa. Look at Eastern Africa there. Hey, there's a couple of hotspots under there. There's another one nearby. I wonder, is it possible that hotspots might help form plate boundaries? Maybe by acting like a blowtorch, cutting through the continent, allowing it to have the possibility of separating, of diverging. Maybe that's a possibility. Look at Yellowstone in America, in the USA. Yellowstone is a hotspot that is underneath a continent. So this causes all kinds of interesting interactions. There are the most geothermal features in the world in Yellowstone. It's an amazing place to visit, and it's very, very volcanic. Notice right next to Yellowstone, there are those red hatched lines. That represents the basin and ranges going across Eastern California, Nevada, and Utah, much of Utah. That is where the North American continent began to rift. However, that rifting seems to have stopped, so we don't seem to be in danger of forming into two different continents. I mean, we already talked about how we're actually on the Pacific plate, but it looks like the North American plate has stopped rifting, but for a while, it looked like it might actually form into two separate continents. This is possibly due, I'm just speculating, that there's only that one hot spot. It's a pretty major one, Yellowstone, but if it just had another friend there, if it had another hot spot, it might have been able to complete the job, like the ones in Africa seem to be doing. So hotspots can be located in the middle of a plate or under a plate boundary. As far as we know, that is fairly coincidental unless they are responsible for forming plate boundaries, which does seem to be a major possibility. If we look at where hotspots are found, it does appear that they are distributed fairly randomly, and this might have something to do with the internal temperatures of the core of the Earth somehow. However, some of them happen to fall on plate boundaries. Maybe they helped form those plate boundaries, and maybe they will help to form new ones in the future. This remains to be seen. Okay, one that we're looking at, of course, are the two in East Africa that seem to be forming the Rift Valley, or at least helping it. And then, of course, we mentioned Yellowstone. But look at those ones in the South Pacific. Maybe that would form a plate boundary in the future. We do not know. So it's interesting to see the effect that hotspots have with plate tectonics. They obviously form major volcanic features on the Earth, but then again, they may also be related to the formation of new divergent boundaries. So that is the end of the notes on plate boundaries. Now notice I did not talk about why the plates are moving, just the way they interact with each other and hotspots. But now in the next notes on tectonic forces, we will get to that. So just hold your horses. We'll get to tectonic forces. Bye.